Hi guys, Mrs. Rossi here. Today we're going to be talking about pH. We previously talked about acids and bases, and this is the follow-up notes that go with that section as well. So you'll see on your pH note sheet, it says to list some properties of acids and list some properties of bases. This is something you should already be familiar with. If you can include some examples, that's even better. As we talk, make sure you're filling in your note sheet. If you need to pause or go back, make sure you do that as well. All right, we're going to start by going back and talking about water. So we know that water has many unique properties. We did a whole section on it. It also plays a huge role in understanding acids and bases. We talked a little bit when we did definitions of acids and bases, what happens when you put an acid into water or when you put a base into water, and we're going to talk more about that today. We know water is polar. We know that oxygen has a higher electronegativity than the hydrogens that it's bonded to, and this plays a big role with acids and bases and figuring out what the pH of a substance actually is. So when a water molecule loses a hydrogen ion, it becomes negatively charged, and it's called an hydroxide. So you should remember hydroxides from when we did polyatomic ions. It's oxygen, hydrogen with a negative charge. And a water molecule that gains a hydrogen ion becomes positively charged, and it's called a hydronium ion. So it has one extra hydrogen and a positive charge. So H3O plus, a hydronium ion. The concentration of hydroxide ions and hydronium ions is super important, and usually a shorter way to write a hydronium ion is just like this. So the concentration of H pluses, because it doesn't take into account the water then too. So writing it as H3O plus or just H plus means the same thing. The brackets on the outside of your hydroxide up here and your hydronium down here mean that is the concentration of them. So you can write this just exactly as you see it. And for this one, this is the concentration of hydrogen ions with the plus, or you can write the hydronium, the H3O plus, but make sure it's in brackets to represent concentration. All right, in any solution, the concentration of your hydrogen ions and your hydroxide ions are interdependent. So they depend on each other. If one goes up, the other one goes down. If the other one goes up, then the first one goes down. In aqueous solutions, so remember that means water-based solutions, the product of a hydrogen ion concentration is always 1 times 10 to the negative 14th, which sounds kind of crazy. We're going to talk about the math behind this, but I just want to take you through it so you know where this pH scale even came from. So what happens is when you multiply your concentration of hydrogen ions by your concentration of hydroxide ions, you always get this 1 times 10 to the negative 14th when you're dealing with an aqueous solution. So in an acidic solution, or for something to be considered acidic, your hydrogen ion concentration is greater than your hydroxide ion concentration. So an acidic solution would have a lot of H pluses in it. A basic solution, on the other hand, has more hydroxide ions than your hydronium or your hydrogen ion concentration. So when this comes back down to the math part of things, the H plus concentration of an acidic solution is greater than the 1 times 10 to the negative 7th, and in a basic solution, it's less than 1 times 10 to the negative 7th. This all kind of sounds kind of crazy with the brackets and the scientific notation. So here's a picture representation. pH, and this is what we use to measure if something's acidic or basic, stands for potential of hydrogen. If something has a low pH, all that it means is that it has a whole bunch of H pluses and not so many OH minuses. So it has a whole bunch of hydrogen ions and not a lot of hydroxide ions. If something has a really high pH, it has a whole lot of hydroxides and not a lot of H pluses, not a lot of hydrogens. So if you look here, here's a chart of concentration. In an acidic solution, you have a whole bunch of hydroniums and not so many hydroxides. In a neutral solution, you would have an even amount of hydrogen ions and hydroxides. And in a basic solution, you would only have a few hydrogen ions, but a whole bunch of hydroxides. So here's the math just to prove it to you so you know where it came from. Don't worry about the math. I'm only showing it to you once so that you can see what it's all about. pH scale is way simpler than multiplying and doing all those scientific notation things. The pH scale ranges from 0 to 14, with neutral solutions having a pH of 7. pH stands for potential of hydrogen, in case you didn't get that before. To figure out the pH of a substance, you do the negative log of the hydrogen ion concentration. So you would do it right in your calculator. And if we had a pH, or if we had a neutral solution, so our hydrogen ion concentration would be 1 times 10 to the negative 7th. You would do the negative log of 1 times 10 to the negative 7th, and you would just get 7. So using the pH scale is a much easier way to figure out if your solution is acidic or basic. So what it all comes down to, and what you actually need to know, is that for something to be acidic, you would have a pH range of 0 to less than 7. A neutral solution has a pH of exactly 7, and a basic solution would have a pH range of greater than 7 to 14. So a 0 to 14 scale with 7 being neutral is your pH scale. Some pHs are also listed along here just so you can get an idea of what's acidic, what's basic, what's really acidic, and what's really basic. Is there a POH? Since we've only been talking about the potential of hydrogen, there is a potential of hydroxide, but it's not really used. So you don't have to worry about it, but I just wanted to let you know that it existed. So here are some more substances, and it has their pH, their hydrogen ion concentration, hydroxide ion concentration, and POH, just for comparison. On your sheet, you can list a couple basic and acidic substances. And then we have some practical uses of what pH is used for. So you may have heard that the soil around our area is pretty acidic, so it kind of controls what plants can and can't grow. You may also have seen different color flowers. In something like these flowers that you see here below, depending on the acidity of the soil, you can even produce different colors. You may have had a stomach ache before and been told to take a Tums or an Alka-Seltzer or something like that. That's called an antacid. It helps to neutralize the acid in your stomach. So your stomach acid is in overdrive. You might have a tummy ache. You take an Alka-Seltzer or Tums, and that's really basic. So it helps to neutralize what's going on to your stomach and get your pH back to a normal level in there. We talked about litmus paper before, and we talked about pH indicators before, and I want to talk about one more called pH paper. pH paper, like you can see, has a range of colors to give you a whole range of pHs for different substances. So you dip the paper in whatever the solution is, and then you would match it up to the scale that you see here or the scale that you see here to figure out an approximate pH for whatever that you tested. On your paper, you can flip over to the back. There's an approximate pH scale, and I wrote in the kind of colors that you would see. So take a minute to answer the questions A through D for number 16, and then you can move on and use all the notes that we took to finish the rest of the worksheet.